talk is more on the practical side, and especially the algorithmic side, and also what's the real applications. So this is a joint work with Andre Maple, and who just graduated and joined company, actually doing this type of applications. Okay. So let me just scroll down. Okay. So sensor network localization, I'm going to talk about, give a very quick introduction. Okay. For this audience, probably people already know what it is. Then I'm going to talk about, and it's the very simple. It's called the steep descent projection method. Which is very, very fast, and also especially suitable for doing some kind of sensor network tracking, because the sensor is moving, and so every milliseconds we need to find what the locations. So it's not going to be static. Okay. So in particular, we are talking about how this application for like tracking algorithms and analysis. Finally, talk about the numerical results, and also could give you some demonstration and effectiveness of these algorithms for these problems. Okay, so you can stop me anytime and ask questions. Okay, so for many audience, probably people already know, and what's the sensor network localization now. Okay, suppose you just have different sensors. This is a moving target, okay, in our network. So they are ad hoc, and they are in motion. But however, we can measure some kind of a Euclidean distance. Okay. So this is a particular Euclidean distance we call the Dij, and it's between sensor I and J. Not all of them are known, but however, when they get closer, we know the distance. Okay, of course, the distance could be noise. So for all those distance, we basically want to find in the coordinate positions. So x1. If this is the 2D, that's just the XY axis. If this is a 3D, then you have a XYZ. So each one is the triples. We want to give them a vector, which is R. For real application, it could be 2 or 3. Okay. So basically, we want to solve these kind of functions. First one we call the anchor free. Okay. So we're basically finding the coordinate xi, that's our decision variables. When we find xj, the Euclidean distance, and then we can only measure square, we don't know the sign. So minus Dij, which is what we measured. We can use any loss functions. Okay, simplest one, just take another square, okay? Or it could be other and the loss functions, which I'm going to introduce. And for these anchor-free ones, and we just wanted the gravity, center of gravity equal to 0. So basically, because otherwise this problem could be unbounded, because xi, xj subtracted by the same numbers, they still maintain the same distance, so they could drift away. So typically, people in practice, they said, oh, they add up equal to 0. So basically, the geometric, the mean has to be at origin. Another one is very popularly used, and which is the anchored. So for these same things, we assume actually we need the LR plus 1. We at least if two-dimensional, we assume the 3 points position already known. Okay. If this is in the 3D, then we assume the 4 of them are already known position. So they serve as so-called anchors. Otherwise, the graph on the network is not it's not uniquely defined. Okay. So this could be for any functions called L. Okay. So as you can see, the problem is generally not convex. Okay. Because this is a square. Okay. And also even the loss function is convex. So there's many applications. Some applications called the phase, because we don't know what's the positive side. We don't know any angle information. So it's the only node pure like a distance information. So for these problems, just like many other distance geometry problems, then you can use so-called semi-definite programming to represent it. Okay. So basically for xi, xj, this is the coordinate. Okay. Once you write down this one, we can use a matrix representation, and which is the U. So this basically write them up, just the UII minus UIJ, UJI, UIJ, JJ. So you just or simply can write a matrix dot product, which is the EI. So EI is the unit vector, only have a 1 at the ith position and 0 everywhere. Okay. So this is the difference between ith point and the jth point. So your dot product, the U now become a known matrix. And basically we assume Uij equal to xi minus xj. So this is an inner product. So because U represent as this form, and that's x transpose t, x is our original decision variables, and you just named up, okay, with this kind of fashions. So this could be, so this is going to be R by a matrix. So once you write this, you put this outer product, then U has to be positive semi-definite. However, if I just replace these variables and linearize these objective functions, now this become a linear expression. And then you have convex loss functions, then this function become convex functions. But however, this matrix has to be, if you want to really recover the original problems, you have to get a rank constrained semi-definite programming problems. Okay. For anchor free, we just say all the one add up equal to 0. U is positive semi-definite. Of course, rank U has to be less or equal to R, which is the desired dimension for localization. Okay. And if you have anchors, that's also doable. So you just add a couple of constraints, and it's all linear constraints. So you basically solve convex functions. And then if you take absolute value, then you can write them as a standard linear SDP. So here's the problems. Okay, so this is the formulation. So of course, and this problem is not new. And so especially for people in this audience, they're all working on the distance geometry, especially Euclidean distance geometry. So this is basically, and it's like inverse problems. We know the distance, we go back, want to find the position or localizations. You can trace back and did manual work. And just say for this particular applications, I just list a few reference. And and one of the student at Stanford, and EE, he did some work on find this first to formulate this problem, because before that, people just use the second order cone or some other relaxation. But then he used this semi-definite programming. Okay. Then it's also get some attention, especially for people in the IEEE. Okay. And also subsequent, Mason Henry also did excellent work. As I said, I just need one reference which can trace back to very rich mathematics related to this problem. It's called, rigidity. So this has been studied also in the pure math, like Professor Bob Conley from Cornell, and also basically analyze when those information, when we give a pair distance information, when it's sufficient, we can uniquely determine the final localization or solutions to that quadratic constraint system. So this is a quadratic kind of system equations, okay? Of course, there was many more, and people are just not, okay, I'm just omit some of those, but they all played a very important role. What I'm going to do today is just, focus on the algorithm side, okay? We can also simplify the constraints, get rid of those linear constraints. So this is, Henry probably knows much better than I am, just do coordinate transition. You can, do this projection, because I'm talking about the anchor free, the mean has to be at 0. Then you can easily down this and rewrite these problems into another objective functions after coordinate translation. Then become just need a matrix V has to be positive semi-definite. Only rank has to be less equal to R. So in this case, the problem become there was no other constraints besides just need to be a conic. V matrix has to be positive semi-definite, and also the rank no more than R. But however, I want to minimize this function. Okay. Well, of course, even we get rid of those linear constraints and the problem remain non-convex. Then, because due to this kind of rank constraints. However, here, this paper, which is algorithm I'm going to introduce next, is based on this fact, okay? So although minimize a general, even a convex objective function, the problem with rank constraint is hard, but however, if you want to project a general matrix into this constraint set, we minimize V, we give a symmetric matrix, we want to finding a V, which is a positive semi-definite, rank is no more than R. If you want to just minimize Frobenius norm, which is the equivalent in vector space like L2 norm, then these problems can be solved very efficient, okay? So basically, you just need to find in the R extreme, the highest eigenvalues, okay? Then just use those positive ones, okay? Typically, factorize a name matrix and completely is very expensive. But however, if you only compute the R like 2 or 3 in our application, extreme eigenvalues, it's the largest eigenvalues, which turn out to be very fast, okay? So, and also you can guarantee the V matrix, you find out, solve these problems. It is the optimal solution for these problems, although this constraint is not convex. So this is already known, okay? So that motivated us to do this so-called steep descent projection method, okay? Some people also call the gradient projection method, okay? So let me quickly, so this is going to be the focus on these problems. So let's consider even a more general problems, okay? So we just wanted to solve a problems, minimize fx as our objective functions. This function can be convex, non-convex. And also, we have a constraint set, call it x, which is can be also convex, non-convex, okay? So in these problems, many, without this constraint, even function is not convex, the most popular method is the steep descent. Okay, so for steep descent method, typically we just need the f to be differentiable. Okay, and also satisfies certain smooth conditions. It's called the Lipschitz condition. So typically we assume and at any 2 points, okay, the function at y and less equal to fx. So this is like a first order Taylor expansion series, but also bounded L, which is called the Lipschitz constant divided by 2, or Euclidean norm y minus x. So in the matrix term, these 2 norms become Frobenius norm. It's going to simply define those. Okay. In the following talk, I'm just focus on analyze how to solve these problems by steep descent projection method. So I usually use X star denote optimal solution for these problems, so-called global optimal solution for this problem. Okay, and again, and the set is going to be a general set. Okay, so I'm going to this. Okay, away from the sensor network localization, but focus on this. So to apply this steep descent projection method, the key assumptions, we can solve this problem fast. Okay, so either by a closed form solution or by very fast numerical procedure, because basically the distance problems. Okay, a general set finding a point in the set which is close to a given point. Okay. So this projection, of course, may not be unique, but that's okay. Okay. So let me just give you certain example. So if this set is a convex set, of course, this become a convex optimization problem. But however, there was also many times and this set and it's not convex, but however, the problem can be done very fast. Okay, so let me give you several examples. Okay. Non-active offset. Okay, so then you have a very easy operator. Okay, you're given a y point, some entry could be positive, some entry could be negative. All you need to do is just zero out those negative entries. So you get the exact projection. Okay. Then if you further assume and the number of entries or the support of X, number of the support size is no more than S, basically mean you want to get X, which is sparse. His non-negative, the number of non-zero entries is no more than S. Well, this is not a convex set, okay? But however, all you need to do is just to keep the largest as absolute value of Y entries and zero the rest, okay? So that's going to be the optimal projection. So this is probably, especially people actually apply this in compressed sensing and which is very popular a few years ago, especially in sparse optimization. Of course, and for SDP, that's also do if you just a simple SDP cone, then you just then the given Y is the symmetric matrix. You just factorize this, keep the only positive eigenvalue part. Now you also have, if rank is no more than R, that's even simpler, okay? So all you need to do is just find in the R largest eigenvalues, okay? If they're all positive, take it what it is, zero out all the rest eigenvalue, okay? Get that matrix. Or if take the largest R eigenvalue, still have some negatives, then just zero out them, okay? And also some lattice, okay? For example, like an integer point, okay? So if you say, if the X represent all the integer point, then what's the projection? Projection is just round Y, which could be a fraction numbers, take some entries and just round them up to the entry-wise to the nearest integer. So that's also can do, okay? Or some other functions, unit sphere, orthogonal, and matrices, all this and can be done very fast, okay? Then, okay, the question is, what's the method? The method is very, very simple. We take a steep descent step, okay? So if we have no constraints, we just take xk plus 1 equal to x, goes the steep descent direction, add some step size, okay? In steep descent method, the easy step size, even if we know L, it's just 1 over L. But here we take a 2L because that's the difference what we took for this steep descent projection method. Then once we get this steep descent projection, okay, then we just project back to the feasible set, okay? So it's like you have some objective contours, you have some kind of like a level set, which is not convex. So you go over there and put the direction, okay? That's the steep descent direction. And then you just, once you get these points, you're finding the closed points or something, whatever, okay? Then you just do this and then project back. So this is your X, okay, the set. So I just want to mention the algorithm. As you can see, this is a very, very computationally efficient. All you need to do is compute the gradient vector, okay? So I want to emphasize, okay, then do the projection. Projection is basically finding a point in the set which is close to this one. The one difference here, and the standard steep descent usually take 1 over L. Even you don't know what's the L, you can still do like, in exact search, you can try L and do some kind of like backtracking and finding L. So this is how people use it in practice. But here I just assume we somehow know this L. Okay, you can try L very large. You can gradually learn what's the L you should put over there. But here what we did is we take half of the standard step size, which actually played a key role to prove convergence for any objective function and any convex set, as long as you can do the projection efficient, okay? So in this case, we project back. So this is typically is called descent first and the feasible second approach, okay? So many nonlinear optimization, they want finding a descent and simultaneously to be descent, but also feasible. But here, we basically say descent is like an alternative. We find the descent, then project back, become feasible. Then we go to descent and then project second. We're not aim to find a simultaneously descent and the feasible direction. Okay. So which is typically very hard for nonlinear, non-convex optimization. For this method, surprisingly, and of course you can, or not surprisingly, you can also go back to the history. Alan Goldstein talk about this method, and Levtin, Polniak, and also, of course, in the USSR formal, okay, also have this method, and later, but this is for convex objective, convex feasible set. They have some analysis, but it's not clean. Always contingent on some assumptions. That's a surprise me. Looks like some analysis should be done long time ago. More recent references, which is also dealing with non-convex objective functions, non-convex constraint set. They also have some papers recently, but most of these papers make some relatively strong assumption about the nature of constraint set and also objective function in order to give some kind of a convergence or convergence rate or some kind of even sometimes linear convergence. So most of the time they have to strong some technical assumption. Also, you have to start the point very close. Then you can prove something. Okay. So what I'm going to do is, I just want to, next few minutes, I just show actually by taking the steep descent with a half of the standard steep descent step size, actually you can already prove a lot of things. Okay. So what's the projection? Projection is basically say, solve these convex quadratic functions subject to x in this possibly non-convex set. So what's this? Again, it's just the Taylor expansion, okay, and the first order, okay, linearized at x point k, okay, finding an x, minimize this linear function, of course, also constrained by the Lipschitz quadratic, okay, like a proximal point, kind of like a regularization. And this regularization is regulated at L, okay, because we only take a half of step size. Typically, people do this with L divided by 2, okay. So now you can see that why I put L over there. Then, because xk, it is in the set, so this function must be less equal to 0, okay? Otherwise, I just take x equal to xk, x equal to xk, this objective value will become 0, okay? Now I minimize this, so this must be less equal to, the whole thing has to be at xk plus 1, has to be less equal to 0, okay? Then by using this Lipschitz smooth conditions, so this function is less this linear term plus L divided by 2. However, because I solve these problems, so this is less than negative L, so negative L, okay? Then you can prove as long as xk plus 1 not equal to xk, this will be strictly decreasing unless xk plus 1 minus k equal to 0, which means you take a steep descent, you project back, you still project back to the same point you start with. Okay, so that's the small trick. So for somehow, and I think this my student Maple is first thought about this idea and prove this. So what's that means? That means because when some function is bounded from below, so this sequence typically would be a gradient vector. If no constraint, xk plus 1 minus hk is just gradient vectors. But however, you can decrease this by this amount. So if this function is bounded from below by fx star, that's what I talk about, okay? Then it's very easy to do. This constraint will be only epsilon square, okay? And with this one, initial or objective difference, function difference, you can create this has to be less than epsilon. Otherwise, it's just if this keep greater than epsilon, then objective will go unbounded from below. So this is very, very simple analysis, okay? Now the question is, what's this vector means, okay? So you can easily see, okay, if let's say this X fits the set is being a non-negative ortho. Remember, I can easily prove. And for this one, it's just truncated. Just remove all the negative point in this steep descent and direction. So basically, you can prove this is less than 0, then dga is just a gradient vector. If this scenario, dga is just a gradient vector. If in this scenarios, okay, dga is just a coordinate. So when this goes to 0, so either this gradient vector for that jth entry goes to 0, or the coordinate of jth entry goes to 0. So which means this is exactly so-called complementarity slackness residuals. And it's like a gradient and project onto the non-negative origin. So this represents a feasible direction and also descent direction. So the point is, when d is small, when these two successive coordinate, the Euclidean norm is very slow. That means d is small, but d is generally represented as the feasible direction in the convex whole of x. Okay, x itself may be not convex, but this because xk plus 1 xk, it is both feasible. So the difference of these two successive solutions represent a feasible and a descent direction in the convex whole. Okay, so then you can easily prove when d equal to 0 and the x is going to be a first order, like a stationary solution. We still cannot claim this is a local minimum, such a thing. That's the typically because you assume non-convex. Okay. Now, let me provide a little bit more analysis. When the feasible set is so-called star convex, and also objective, it is a convex function, which is true in our applications. Then, again, we use these Lipschitz conditions. Then assume x star is the optimal solution, global optimal solution. So here I'm just assume my feasible set is going to be x star, which is the global optimal solution for this problem, so-called star convex. So what's the star convex? So that means for any feasible point x in the set, okay, then the convex combination of these 2 points. So you always aim at x star, which is the global optimal solution. X is any point in the set. This line segment is also in the set. Okay. So we're not going to be assumed for any given 2 point, the line segment in X is all the point. If they connect to that global optimal solutions, then it is in the set. Okay. So in this particular case, what we can do is we can provide a bound for these problems because xk plus 1 is the lowest, is the closest point to that one. So then it must be do better than any of these point. Okay. So that means this one is going to be bounded above by any alpha between 0 and 1 for any points on this line segment. Okay. So if you substitute this line segment into that quadratic functions, so you basically this is going to be less equal to any alpha, which is okay. And with these 2 given points, although we don't know where x star it is, but actually we can do this for analysis. Okay. So what you can do is, well, if this one is less than this, instead of use our naive and the bound, we can actually choose the optimal alpha, minimize these functions. Okay. Actually, if we assume f is convex, so this one is going to be a negative term. So this quadratic function choose alpha to minimize this one, always have a positive root, okay? So we just choose this, and this is going to be the root, okay? If this one bigger than 1, of course, we choose 1, and then you already get optimal solution because alpha has to be between 0 and 1. Now what you can do is, you can say, oh, this one actually is bounded by this term. Again, you can see now, okay? So the function is strictly decreasing, okay? So xk minus fx star, which is the square, and also 4L, which is the x coordinate, and this is the 2 norm, okay, and to the optimal solution, which is very typically appealed in steep descent method, okay. So then what you can do is, because you have a reference for this one, then you can show now in this method, not epsilon square anymore, only epsilon. Then take another log, initial difference, become epsilon. Then you can prove fxk minus fx star, which is less than epsilon. So this is a little bit of surprise to us because all the previous result, even for the convex case, is the epsilon square, which I talk. So in this particular case, what's the delta? It's basically the diameter of the level set. You start a point and fx0, because you generate a point always in this level set. So basically, and the diameter is the biggest difference between the Euclidean distance between 2 points in the set. Okay. Now you may say, is any application for this case called the star convex? Well, so I just star convex set also appealed many things. Generally, for example, all the non-convex cones are 0 star convex because they all contain the origins. So take any point in the cone, connect the origin to that point, and is entirely in that cone, if that cone is not convex. Now we go back to see people studied in compressed sensing. So if you think of X star is the S sparse optimal solution for some kind of regressions, then X is the set of all D sparse. D actually could be greater than S, okay? But as long as the support X star, which is those non-negative component, which is contained by X. So it's like you have a very sparse solutions, only have 2 entries, okay? All the rest are equal to 0. But however, you may have another vectors, only ranked 3. But as long as those 2 of these support X contain in that, then you can get other non-zero entries, okay? So those, as long as this matches this one, it's going to be star convex with this X star, okay? So it's like combinatorically, at least as a support X star X, then you can constrain the X by any rank more than S. So that X still to be a star convex with respect to the sparse solutions, X star. So that people have proved a lot of compressed sensing result use this related method. It's called a thresholding method because when we project back, it basically do some thresholding, only keep those largest component in the coordinate, okay? Furthermore, if we have F is strongly convex, so that means this complete is true, which is also bounded by smallest positive eigenvalue of the hashing, which is bounded by this one. Then you can prove this has a linear convergence rate, which is also consistent with steep descent without any constraints. So it's going to be steeped by these ratios, okay? So very, very interesting. All the literature in this one when they assume strongly convex, they only can prove when the xk plus 1 close enough. Okay, there were also some reference in the compressed science literature. They prove it possesses some kind of a linear convergence only when L divided by gamma, which is the convergence ratio of this one, which is less than 2, because some kind of a special structure, the technique they used in the proof. But here you can see, as long as gamma L is bounded, okay, and you have this so-called linear convergence rate. Okay. So one was is a very simple, very algorithms, which is basically use a steep descent. Then as long as we can do this projection back to the feasible set efficiently, either and convex, non-convex, you all guarantee convergence. Typically, you guarantee 1 over epsilon square. But if you are convex, you have 1 over epsilon. But if you even and assume a strongly convex, then you actually have a linear convergence rate, which is basically give you a log 1 over epsilon to prove some epsilon accuracy. So that's the method we do. Okay. So now let's go back to this reformulation as a SNL problem. So and that's exactly what we have. Okay. We want to minimize objective functions. Okay. Which is V only positive semi-definite. Rank is no more than R. Okay. So we apply this method. We're finding a distant descent. Okay. Then we just project back. Okay. The gradient projection for this particular science localization objective is very simple. Okay. So I'm going to very quickly go through this. And you can write what's the adjoint and write this objective function. That gradient vector itself is going to be a symmetric matrix, okay, but not necessarily positive definite. We take and along that direction, then we'll project back. Okay, so each time we'll only need to keep R rank positive semi-definite matrix coordinate. So that not only makes them project back to still bad, but also saved a lot of computation, especially saved a lot of storage, because instead keep the full and symmetric matrix, or only keep that matrix in product form with no more than rank R. Okay. So this is an algorithm, which is, as I said, okay, you only factorize R eigenvalue, eigenvectors, okay. You only need to do these projections, okay, this project back, okay. We also did a little bit, once we get this coordinate, we also do some scaling, okay. And so I'm not going to get too much details. It's basically, it's become a one variable problems, okay. In somehow not only finding a best step size, but also finding what's the multiplicative factor scale of numbers. Okay. So then to analyze this scaling step, you can prove they can much better guarantee the final solution meet the first order conditions and also meet the positive, especially gradient vector. At the end, is going to be positive semi-definite. So especially when we analyze without rank. So this is what our without rank constraints, because for a lot of this science network localization problem, if you don't add the rank constraint, so optimal solution for this one is already the desired rank. So this is related to the global rigidity I just talked about. Faki and also did work and related to some kind of a universal rigidity concept. Okay. In practice, what we also do is instead always keep R of them. Actually, we start with high D and then a dimensional we keep D, rank D, but gradually reduce them for R. Okay. So those are many practical tricks which is make this works. Okay. This just to show you, and the final solution is going to be stationary solutions. Okay, and let me about 10 minutes, so I'm going a little bit fast because I want to give you some demonstration. So those getting fact. So here's the examples which I'm going to give. We generate instance SNL problems with chosen like equal to 100 points or 50 points in the grid, okay, and -1 kind of a square. We do 2-dimensional. Then we also add some kind of a small noise to the algorithm. Then we try to find what's the final solution. We use RMS error, which means the truth locations. However, distance was a noise, and then it's the final output of the solution. So the algorithm solution we term as a recovered. So we just use this as errors. I think many people ever do. Of course, this is just a picture just to show you. Okay, depending on the noise level, which is the reasonable. Okay, so this is the errors. Okay, as you can see, and this is put against the radial range. So what's the radial range? Radial range is the assume when 2 points whose distance is below this range, we can measure the distance. Okay, then we add some noise. As you can see, when the range getting bigger, that means I have more information. I have more edges, which is the DIG. Okay, we can find what's the optimal solutions. Okay, so this is SL. So as you see, if we keep this noise level at the same thing, if more edge information are known, the distance information are known, then the error become smaller. Okay, so this is one which is not surprising. So this is for given a range, then we see how the noise, okay, and add errors, which is increase. That's the true ones. And we did basically the error was increasing. So this is also, since we do this simulation result, each time we run multiple runs, so the error could be around this. Okay, this is the average error. So this is the standard deviation. Okay. Then we also test on different noise functions. So typically square, that's the people most popularly used. Okay, with also different. This is the Hooper, this is the Cauchy, this is the Welch. Welch means you flat out. Okay. Then also against did this kind of error analysis as the perturbation increase. Okay. But what I wanted next to show is this method is particularly effective as the poster solver for pure SDP relaxation without rank constraints. So this is what I want to show you. Okay. So typically we're going to run this. Okay. We start from this. We run SDP relaxation. The solution come out may not be the ideal rank, but however, we use the output that SDP relaxation solved by some more sophisticated SDP solver. Then we use this low rank projection as the poster solver. Okay, so I want to give you some demonstrations, which is the MATLAB. Okay, so what I'm going to do is I'm going to show this. I have, let's say, I'm going to use this. What I'm going to do is I give 50 points. Okay, I'm going to let the radial range to be 0.3. Okay, suppose I add no noise first. Okay, and just do simulation. Okay, I have randomly generated points. I use the first 3 as anchors. I'm going to do in the 2D. I want to localize 50 points. I set the radial range equal to 0.3. That means every point, 2 points whose distance is below 0.3 and know the distance. Okay, so we have something of this 8 is not that important. That means only keep at most for each point, keep at most 8 kind of a distance information edges. So I want to show you some pictures. Okay, so this is so these pictures. Let me just show this picture just to show if you just solve the original problem, it's not ideal rank. So basically, you have 2 rank more than necessary from SDP solution. So let me give these 2 points. Can everybody see my pictures? So this is the solution. So let me explain. What's the greens? Green is the true solutions. Okay, of course, the algorithm does not know. The red star is the point generated by the algorithm. So the first picture indicates the solution generated by standard SDP relaxation without any rank constraints. It turned out for these problems, and we want rank equal to 2, but however, the solution come out is going to be rank 4. Rank 4 means there was 2 points. It's not accurately localized. This is the true position, but this is the generated by the algorithm. Okay. So once we get these rank 4 solutions, we use this rank 4 solution as the starting point to apply this steep descent projection algorithms. Because this is only rank 4, we start from rank 4, we continue to do this rank projection. After 100 steps, we stop. So this is the solution come out from that after that steep descent kind of projection method. So this is the solution which you can see, and they actually get out to this point. Okay, so that means this procedure, steep descent projection method, will get the ideal rank solutions pretty fast, as long as the starting point is very, very good, very, very close. Okay, so this is the something which we used for ideally for a lot of problems. Let me give you a couple another rounds. Okay, so for example, I can generate 100 points. Okay, I can generate and also give some kind of noise. Now I have a noise. It's the 10% multiplicative noise, which is added to the problems. Okay. So the problem a little bit long to solve. So this is the after, because they have noise. Okay. So this is the last picture, which is the after steep the descent projection. So this is a picture and before with just after SDP relaxation. So you can think about this. So this is right after SDP relaxation without any rank constraints. So this is solution, use this as a starting solution, and then do this project gradient and minimize, try to get the best low rank solutions. Okay. Again, you can compare the solution quality of this picture and this picture. So that's my point. So if I don't have this as a good starting point, get this solution, start from a naive solution, it's very, very painfully slow, but also not get as quality as this, because because this is non-convex set, okay? And the rank constraint SDP set is not convex. So we can not guarantee finding a global solutions. But here, so this is very good. Okay, so let me stop the sharing of this MATLAB. So let me just go back to this. So what's that means? So that means this method is particularly good for tracking. So as now we can get a very good initial solution. When the problem's sense is moving, then we can always use the previous solution as the starting solution to apply this steep descent projection, because we, in the real time, they have to do this for every like milliseconds or something. So you don't expect the new localization is too different from the previous one, okay? So that's very, very effective, okay? So this problems has to be so very good at tracking, okay? Okay, so this is, I'm just show you some pictures, okay? So you can do this tracking very, very effective. So just, you know, you can also do the 3D, okay? So this is something I want to really emphasize, and for this particular talk, which is I'm very, very excited, it's called the satellite cloud tracking. So let me give a little bit of background. What's this problem? This is a real problem, okay? And sensor localization has been successfully used. Imagine a company launched hundreds of satellites in the orbit. Sometimes those satellites may move in not as controllable as you like. So their position may be unpredictable, you know, especially they have some failures. The only thing they can do is they can measure the relative distance between satellite and satellite, okay? So then they have to localize. So they have to keep track of all the satellite, how they movement. Okay, we just heard the news. There was China's, you know, satellite falling on the ground, and nobody can trace them because they're completely out of control. So this company, which is the Maple is working now, okay, is actually apply this in the real satellite cloud, okay, tracking. Probably people don't know. Our sky is getting very, very cloudy, okay? People talk about the communication network, just complete immediate ground wires of communication, just use satellite. So they launch a lot of satellites into orbit, okay? Then tracking them and localize them become very important task, okay? So this is, I'm just very excited to hear the news and also finding what we're all doing here and the distance geometry and also sensor localization really found a real application. And also they found this SDP, especially low rank algorithms, actually significantly outperform all other like multi-scale algorithms and all other old technologies. So with this, I'm just stop. Okay, I'll be happy to answer any question. Henry, thank you.
Thank you very much, Yinyu. So nice theory and application. Yeah. So we have some time for questions. Yeah, you can ignore my question.
Okay.
You answered it immediately after I asked. So.
Okay. Yes.
So can I have two questions, please?
Yes.
Yes.
First, if I understand it right, if you have noisy data, it may happen that the solution to your problem does not exist. Isn't then the projection, the lowering projection, to have a tool? You know what are you getting then by the projection?
I always have a solution. It's just the solution may not be accurate because I minimize those like a chordic polynomial function, which is in standard is called the least squares. So the problem I just showed is if you just without rank constraints, the solution come out, which is more have very, very large errors, because when you minimize without rank constraints, you get a solution. The best solution may be minimize that same cost function, objective function. And the rank is very high. When rank very high, then it's much worse than the optimize with the rank constraints. So the picture I showed is one is without any rank constraint, another with rank constraint. So yeah, so then you can see the quality with rank constraints optimal solution is much better than the previous one. Okay, without rank constraints. So a lot of.
Sorry.
Go ahead. Yeah.
Would there be a big difference if you just take the SDP solution without rank constraint and project that solution without doing the steepest descent?
Yeah, this is already projected.
This is
already projected.
Okay. All right.
Yeah. So the picture I showed you exactly what you said. Okay. Mm. So this is already yeah. Otherwise, you cannot see it. So this is a direct projection. So I get a solution. I choose them not just basically because our SDP relation. This one has anchors. You see, they have 3 anchors. So I just take that coordinate, use anchor information, project back in the rank 2. So that's the picture I showed you. This is the best rank directed. But this is you can think about this is a back. So you can think about this is just a one-time projection, but this have 100 project adaptively. Okay, continue to do this steep descent projection. Finally, after 100 steps, that's the final solution. So you can think about it. We take this solution, some further minimize and with rank constraints. Yeah, that's good. Yeah, point.
Okay, I see. And sorry, the second question, the general one. So you said you are projecting on a non-convex cone or non-convex set, and it may be that the projection is non-unique. Yeah. Can that be a problem for the method?
Yes. But right now, from our theoretical analysis, there was no need for projection has to be unique. Okay. So you can choose everyone.
Can't you like some sort of zigzagging or something like that?
You could have zigzag, but however, it's just a slowdown. But however, our convergence speed is still maintained. Okay. It's maybe with a unique projection, actually the real performance was much faster than the worst case analyzed by the theorem. But however, we find that the unique or not unique is not. And also for this particular problem, the projection always solve a strongly convex function. So in some sense, maybe for this particular objective function, the projection, it is unique because although the set is not convex, but however, the objective function is always strongly convex.
Okay.
Yeah.
So I can imagine you can get non-uniqueness in case of multiple eigenvalues. Let's say the second biggest eigenvalue is multiple eigenvalue. And
oh yeah. Yeah. That's right. So that could of course that could happen. For our sense network localization problem, because we do have some noise data and we assume the noise randomly for this simulation is randomly generated. Yeah, we did not have that particular problems. We always, there was no multiplicity in the eigenvalues. But in practice, you're right. And maybe for some kind of like a specifically designed examples, you have to choose which, you have a tire situation, which the best 2 rank you choose. That's right. Okay.
Thank you very much. So I like this trajectory projection, or this trajectory tracking.
Thank you. Yeah. Yeah.
Can you say something about your method? Sort of reminds me of a splitting, because you're doing the objective function first, and then you're doing the projection.
Yes.
It's almost like a splitting, which allows you to handle a non-convex. Did you think of it that way? Or?
Yeah, I think you can think about this like alternating kind of a method. This particular alternating method, that's right. You can see it's like a splitting algorithms where one is to generate a copy of that one, and then you minimize that one without consider feasible set, and then do the second one, consider the feasible set. Yeah, you can think about it that way. I found this methodology, maybe Henry know better. This is the same started in the 60s, and but however, they are gradually out of fashion because not much analysis has to be done on this. Then people, of course, also talk about the gradient projection. You can direct project into some kind of null space. Then the problem become actually feasible direction method. So there was some overlap, especially handle non-convex set, which is probably there was not much application then, so it's not gained a lot of attention. But you can see still good people which actually do those things project. Yeah, it is that in terms of it is like splitting in terms of alternating kind of things, finding a point in the set, find objective, we split objective and constraint set, like two type of concerns. So we address first concern, make those deep descent. The second one, we just project finding a close point. Because for augmented Lagrangian method, you can think about this as one. But augmented Lagrangian method mostly analyzed for like a convex. That's right. That's a good point. Yeah. I've not think about that.
Any other questions?
Good. Yeah, as I said, particularly exciting and actually has been used. So this actually become the company started build a special team. It's called the Science and Network Localization team, actually within the company.
Is
and my student is one member of that team. I cannot reveal too much because right now that's the top secret for the company right now. Yeah. So, but we have a full paper. We're still waiting for the final approval. Okay. Of course, only use the synthetic data. So that's why I could not show you the real satellite tracking like pictures.
So I learned about sensor problem from Michael Saunders, PhD student.
That's right, Holly. That's right.
Holly.
Yeah.
She's not. Yeah. She's not a member of your company.
No. The company I just mentioned is the company able to launch a satellite to the orbit. They must be big company. So it's not like Holly. We just did some. She had a startup and do something, but the company I'm talking about is the giant.
Oh, okay.
Can you say at least how large are these problems in the company, the practical problems?
Say again.
Do you know at least how big are the problems, the practical one in the company?
Yes. I even don't know that information. But however, I imagine, you know, if you talk about satellite tracking, and people usually, I don't know how many GPS, for example, GPS, how many satellite, I could be in hundreds. So it's not like a huge amount, whatever. It's like, you know, people build this satellite network, talk about the launch about, you know, few hundred satellite. That's my guess.
One of the big problems now is to clean up all the garbage out in space.
That's right. They also have a lot of garbage over there. So actually tracking those garbages itself, you know, and of course people use radar or laser or something, actually try to tracking those object distances. Yeah, because for this company, you know, they need keep an eye on those satellites on 24 hours, you know, every second they want to trace them.
So if you're doing it for satellites, do you have to worry about the theory of relativity?
I think so for those kind of things, they basically what depending on how you measure the distance, they basically have to do some kind of like a data, you know, because gravity, because the moving, the motion, because the, you know, curve, the distance, or, you know, all those kind of things. That's right. They have to convert them into some kind of like a straight line distance. So they already do those kind of things. So after they clean all the distance measurement, of course, they make sure they really represent the straight line distance, and then they use this and put it up there. But during the measurement, yes, but that's beyond okay, things. Actually, the distance value. So right now, I put a 10% distance noise. The things are still working very well. But if you have a very, very low data distance, then things, you know that, I mean, yeah, the things become very, very bad. That not much you can do, because, you know, once you have a garbage in, garbage out. But however, they have technique to measure those distance, kind of relatively accurate. So they find this accuracy is much better than other methods.